Okay, so it's on the half hour, so I guess we better start going. Thank you all for coming. Amazing turnout for a data modeling language and protocol walkthrough. I wish they could have a bigger room. That would be cool. So my name is Carl Moberg. This is a follow-up session from Nanog 61. It is slightly updated. And actually for you guys, we have two sessions today. So the first one that I'm going to start in on right now is a technology deep dive. We will cover the Yang language and the NETCONF protocol in some detail, actually. And I'll let you go for lunch, or a brief lunch. We have about 30 minutes between the sessions. And the second session will be all examples. So I will literally only have a single slide compared to the 75 or so I have in this session, and the rest will be spent in my terminal window. So depending on what you care for, both probably serves their purposes. For those of you who were here for the kind of the similar presentation from Nanog 61, this is kind of the same. I'm going to use it as a level set, so none of you guys actually hit the next session without knowing what I'm talking about. There's only been a few updates around the models that we're going to talk about in the standards, and a couple of things related to the protocol. Otherwise, it's going to cover much of the same basis as here. And let me try the clicker. Good. And as I said, the next session will also use two protocols, NETCONF, and actually we'll look a little bit on the RESTconf protocol, or the protocol that will eventually be called RESTconf in the next session for protocol level examples. Okay, so let's get started. And I would strongly urge you guys and girls to ask questions. Otherwise, this won't be a 90-minute presentation. It will probably be a 60-minute or so presentation. So either raise your hands and scream, or be good citizens and walk up to the mics. I don't think we're going to have any lines, so I don't think ordering or order at the mic will be a huge problem here. Okay, so let's get going. So first of all, I usually start these presentations by kind of level setting of what we're talking about. I have worked around network configuration and network orchestration since the late 90s. Unfortunately, not much have changed over time, so just to get us all started, we have to realize that we're all battling at this point in the entire industry the following incumbent market leaders in configuration management. I moved to the US about 2 years ago. I've been traveling to most of the large companies that own and run networks, and I'll tell you that 100% of them, without a doubt, actually sit in swivel chairs and type things into their CLIs or craft interfaces based off of content in Excel sheets, Word documents, or stuff that comes out of printers. So we're trying a very modest approach here. We're trying to start from nothing and go to somewhere. So it's not a super forward-looking post-SDN presentation. It's going from where we are right now into something that is incrementally but noticeably better. So I'm going to go through a brief overview, kind of a background and motivation of these technologies, go deeper into the NETCONF protocol, even though most details, most kind of PDUs, most packet content will be deferred to the next session. But I will spend quite a bit of time on the Yang language and its constructs, and we will of course leverage what I tell you in this session. In the next session, we will see things actually going over the wire. So the origins of NETCONF and Yang, okay? So actually the kind of saga or the story about this is that there was a race of hands. Or let's go back to the IETF meetings. What used to happen during IETF meetings was that a group of service providers would meet on the Sunday before the IETF and discuss how to keep the internet alive until the next IETF, which was a good meeting to go to if you wanted to understand what was actually going on in the operational sides of the internet. At a point in the very early 2000s, late 90s, there was a race of hands around whether people were using SNMP for configuration or no. And when the IETF or the IESG realized that there were no usages of, or significant uses of SNMP for configuration purposes, they realized that there was a gap, right? There were no standardized protocols for programmatically changing configuration. SNMP had the features for it, but no one used it. So there were several meetings. Actually, the ITF created a bit of a roadshow and went to several meetings, including Nanog 22, Right 40, and a couple of others like Lisa's, to talk to service providers and people in the know about the requirements for such a protocol, for what could become a useful protocol for programmatically changing the configuration of network elements in distributed networks. And they then held actually a workshop during middle of 2002. And this workshop actually produced a very, very useful document. It's RFC 3535, and we're going to talk about the contents of that, but I will strongly urge you to read that. It is a horrible reminder that the world looks today like it did in 2002, and it very much in detail points out the shortcomings of the operational processes that we have in place largely, and the technology that we have for its underpinning. It's still very, very relevant. So it's a very good read. Here are my personal favorites from 3535. Let's use that as a starting point. These may sound like very basic assumptions, especially for someone with a computer science background, but they haven't really held true until the combination of NETCONF and Yang that are now becoming something that you can find in actual running code came to fruition. And the first one is to make a clear distinction between what's configuration data and data that describes operational state and statistics, right? If you think about it, previous protocols like SNMP and others didn't really make a big difference between them. So for example, if you wanted to back something up and put it aside and then roll it back, you would actually have a lot of data in that backup that didn't actually cover configuration. That was actually statistics or immutable operational data. We would like to think about the configuration of the network, and you'll find that's why we call it NetConf, rather than simplistic device-by-device configuration. We still have some ways to go here, but what we're going to talk about today is the underpinnings of such an effort. So instead of thinking of it as a set of discrete data sets that are not interconnected, we want to think about how to provision or configure distributed networks. Transactions, which has been around in computer science since, I'd say, early 70s or something like that, is such an obvious choice for distributed domains that it's hard to realize or understand why we haven't had it for networks before. And of course, transactions in the distributed domain that we call networks has everything to do with promising the end user or the provisioning system that either the entire change set happens over all the network elements, or we're back to where we were. Such a fundamental feature could also not be found in the traditional or historical configuration protocols or configuration features that we had implemented in these systems. And as a kind of corollary to the distinction between configuration and data sets, a primary mechanism to back up configuration and to be able to roll that back sounds like a very compelling thing to have for large networks. And database schema, a declarative way of describing what the network elements can or can't do in terms of configuration, statistics, and operational parameters, so that we don't have to have reverse engineered and perhaps even offline libraries of models like we did with SNMP or SNMP MIBs in the SMI language would also be good. So again, these are my favorites from 3535 that reflects the conversations that were had with service providers at the time. And again, a reminder, this was 12 years ago. So what the way we want to think about this is that NetConf and Yang, again, the topic of this first presentation, is what came out of, let's say, three pressure directions. Of course, people had a lot of practice or a lot of experience with using CLIs. So the structure and semantics of CLIs is forever ingrained in our operations team. So it is something that we want to learn from. Again, there's a lot of operator requirements at the time that were very well described and covered. And we actually had quite a bit of people that had a lot of experience with SNMP. For those of you who remember, there used to actually be a kind of a restart project for SNMP or for SMI called SMI-NG. So there was a lot of good experience that had gone into that project that we could leverage and bring into the NetConf and Yang efforts in the IETF. So these three things, operator requirements, CLI best practices, and the experience from SNMP was largely the base of which we started building NetConf and Yang on. So first of all, the NetConf protocol. So what we're talking about here is a protocol that is specifically designed to manipulate configuration. So it's an IETF protocol. It has the distinction between configuration and state. It actually has this concept of multiple configuration data stores. We'll get to that in much more detail. It can validate configuration changes. You can actually ask the distributed elements to do that for you. It actually has as a primary feature configuration state transactions, so that two-phase commit-based transactions that we want are all based on primary features in NetConf. It actually does really well in selective data retrieval, so you can use either a simplistic filtering based on paths or XPath to retrieve data here. There's actually event notifications, not to be confused with SNMP traps. It's more of a selective and filter-based retrieval, more of a pub-sub approach, if you like. And it's got an extensible remote procedure call mechanism. There's a number of things that we do in operations that is not all about reading data or configuring things, but actually performing or executing stuff with side effects, like rebooting or pinging or trace routing. So that's all covered by the protocol. And the reason why we think you should care, of course, is that this is the first real good and well-designed protocol that we've seen coming out of the internet community that actually cuts to the heart of all these features or all these requests that we have in RC 3535. And it can definitely provide the fundamentals for a very nice and useful and robust programming environment, right? Because that's where we're going. We're going to have software do these things and not humans. So the Yang language, of course, when we had the NetConf protocol, we realized that we needed a way of expressing the syntax, structure, and semantics of the data sets that we could manipulate using NetConf. So we went hard to work on that, and the Yang RFC actually came to fruition in 2006. The first criteria for the Yang language, well, the first criteria was to prove that we couldn't use any of the current, at that point, current schema languages, like XML schema and others, because they weren't really well designed for this particular domain, and that took quite a while. But the main criteria for Yang was actually to be human readable and easy to learn. So it's a language where you're not supposed to be required to have an IDE, to have some sort of visual support to edit or manipulate it. So compared to things like SMI, and for that matter XML schema, you're supposed to be able to do this right in your preferred text editor. While that may vary, you're not supposed to be required to use anything with visual support. It's a hierarchical configuration data modeling language. There, I invariably get into discussions with people from the object-oriented domain. Now, the reason we went for hierarchical configuration data is that that is probably the best way of reflecting the way routers, switches, and different types of network elements today store their configuration data anyway, right? I've yet to find a router, switch, or a data plane that actually has object-oriented representation of the configuration state, right? So while we could have gone there, this was a pragmatic approach to the way the world looks like. We will forever, of course, battle people wanting to introduce object orientation here, but as long as this works for us, and it does, this is probably the way we're going to stay here. That doesn't mean that we can't have higher abstraction languages on top of Yang that may leverage object orientation, or it doesn't mean that we can't take object-oriented models and translate into Yang, but it does mean that Yang is a tree-structured language. Extensibility through augmentation. As you guys can imagine, there was an interesting conversation around this when some of the incumbent vendors realized that this could eventually lead to standardized models for configuration of basic router and switch configuration, such as interface configuration, IP configuration, RIP, OSPF, BGP, MPLS, and all that stuff, right? And of course, a requirement from these incumbent vendors was the ability to be able to extend all these data models with their own particularly more important extensions that makes things a little bit more valuable. So we have a very strong augmentation system. So you can actually place, definitely place extensions very flexibly across the tree. We'll go into much more detail over this presentation. Formal constraints for configuration validation. It would be cool if a language like this would allow for offline validation to the extent that we can allow it to without bothering the actual network elements themselves. So we could be sure of, or some sort of sure of, that the configuration that we're sending or suggesting to the box is reasonably pre-validated. There's always going to be local context-specific constraints to the router or the switch that we can never capture semantically in a language like this, but much of the type systems and the structures and the relations we can. So again, this would actually relieve the burden of many of these things from the devices themselves. And of course, we need data modularity through modules and submodules. People are going to go to work on this, and of course, things like types and groups of sets of data. It would be great if we could reuse that. We'll talk about that also in more detail. Versioning rules, it's something that have been biting us forever with SNMP. SNMP, or the SMI language, never had consistent and well understood versioning rules. So it was always impossible to understand whether the MIB you were looking at was actually what was running in a particular box. Yang took a good stab at that, and we have very strict versioning rules, and also actually rules for upgrading or downgrading or shifting between versions. And the reason why we should care about this, of course, is that the whole idea of having a full and formal contract language from the device to whatever piece of software that wants to manipulate its state is a pretty powerful concept. It allows for reduced integration costs. It allows for a lot of cool things in the software domain. And since it's also something that you can actually query the network elements for, you can be very reactive and very agile around these things. So it's a very promising technology, I would say. And right now, I don't see many competing suggestions, and there's a lot of traction around this. So I think Yang really has a good opportunity to make a significant and lasting change in the way we think about these things. Now, here's one thing that usually trips me up in shorter presentations, so I'm going to go through it in some detail. It's perhaps not trivial, right? There's a big difference between a data model and a protocol. So in this case, the Yang language is what we're using to write data models, right? And data models describe sets of permitted data, right? It's like SQL, or for that matter, XML schema. It is precisely determines the set of data that is valid according to the schema. So in this case, when we think about these, data models are something that are implemented on the device that we're manipulating, on the device that we're configuring, right? And using that data model, it will check its input data for validity. A protocol provides primitives. It provides verbs, if you like. It is something that you use to manipulate the configuration or the state data that actually resides on the element itself. And the encoding of this data, the content of the data, is then constrained by the model or defined by the model, okay? Now, one false corollary that I come across quite a bit is that it is not necessarily true that you can use the models to validate protocol message content. So things that come flying over to the device in PDUs, right? Let me take an example. Might be the case that a particular device only supports a list of, let's say, 10 security rules, right? That would be a horrible implementation, but this particular device only supports 10 security rules. That box is now running with 10 security rules. And someone is using a protocol, maybe NETCONF, maybe REST, to suggest the addition of a new one. If we're only looking at the protocol content, the content of the PDU or the frame that's coming towards the device, we can say nothing about the validity, right? Because we have to take in the totality of what's in the box, which, by the way, is already full, and what's coming over the wire, okay? So in this case, the model would tell us, no, you can't add a new security role because the instance data already has 10 of those, okay? So bear in mind that the model that describes what's on the device cannot necessarily be used to validate the content of protocol messages. Everyone looks relieved and enlightened. Very good. Also, another thing that kind of trips me up at times is the definition or the difference between information models and data models, right? There's a great RFC, again, it's, no, that's actually wrong. That's not 3535. It's another one. You guys will have to Google on the title. It's on the difference between information models and data models. So information models, and a good example of this is when people use UML, for example, or anytime you see someone at a whiteboard writing boxes and arrows with names on them. That's an information model. It usually describes relationships between things. It usually describes multiplicity, but not to the level that you can implement things. Actually, you want to keep information models on a level where you can't implement things because you want to allow for different implementations of your information model, different protocols to implement the same thing. Data models are tied to a particular implementation, a particular protocol. So in this case, of course, the data model language we're talking about today is Yang. Many standards organizations use informal data models like UML to describe kind of the backbone structure of what they're trying to describe. Things like MEF and Cable Labs and others use information models, and then they have a variety of mappings into data models. Yang, being a data modeling language, is supposed to be complete enough for an implementation for a particular protocol. And of course, today we're going to talk about NetConf and RESTconf. Okay. Protocol layers, another thing, right? So there's a number of protocols that have been kind of associated with network management over time. The four I bring up here is SNMP, NetConf, SOAP, and REST, okay? They are different things. SNMP and NetConf are semantically rich protocol stacks for very precise uses. SNMP has great use for fault and performance. I believe NetConf, again, has a good set of features for changing configuration. SOAP and REST are general transport mechanisms for many types of uses. They don't carry any semantic meaning. You can implement NetConf-like protocols or SNMP-like protocols using SOAP and REST, but you can also implement many other things. And so the kind of thickness of the stack here is vastly different. So if you're looking for something that is particular to network configuration, you will probably be looking for SNMP or NetConf. If you're looking for a general transport mechanism, then SOAP and REST is probably what you want to look at. So putting this all in context, of course, this is what it looks like. You have the distributed domain. You have network elements. They hopefully implement Yang modules. They expose a NetConf interface. Then you have management applications, and this ranges, of course, from very small things like scripts and Python libraries, all the way up to full-blown network service orchestration or configuration management systems that are aware of the models that are implemented by these devices. And that's kind of the contract loop, if you like. And if something changes on the network element side, Yang models get updated. The management applications have means of updating themselves when they figure out that something has changed. That's kind of the entire context around this. I always also get this question, what about $proto? Maybe someone has a particular liking to things that exist like OpenFlow or things that doesn't exist like I2RS or whatever it is, right? And my usual question back is that it depends on what you're looking for. So if you're looking only for a transport protocol, then yes, HTTP would be great for you. If you need a transport protocol with RPCs, well, okay, look at REST, right? REST actually has a couple of verbs, and it's fairly well understood how to do things with that. If you need operations on top of this, which means protocol semantics, then NetConf or SNMP is probably good. And if you actually want something that describes the content, well, then you need a schema-driven protocol, right? You need something that describes the content on top of it. And this then varies over the types of protocols that people will throw my way. So it depends on what you're looking for. So deep diving a little bit more. So again, we're going back to the assumption or the realization that SNMP had failed for configuration, right? Extensive use for fault and performance. But we realized that people were using the CLI. As much as we didn't like it, that's what they did. And that's how, at least a couple of 2 or 3 generations of network engineers were trained using the CLI. So that tree structure, that kind of command or data-driven approach Not only was what people were trained on, it was also the way routing stacks, entire routing and switching operating systems worked. And a huge thing that kind of came out of that is that there is still a very large set of resources that are spent on the way we integrate our network elements into something that makes use of it, right? So the assumption currently is that there will be human interventions between any network device and upper layer management software, right? And you will actually have either humans typing things in, or over time have software developers that kind of reflect the human-to-machine interfaces. So it would be cool to have something that was designed for ease of use, to reduce the amount of effort or resources spent over the life cycle of your network in order to just keep it humming or keep it doing what it should do. So ease of use is obviously key here. And again, I can't begin to tell you how important this is. Clearly separate configuration and state data. That gives you rollbacks, that gives you backups, it gives you the ability to compare data across devices. It's just a very fundamental feature here. Again, we want the underpinnings of something that we can translate into service configuration. There's something that would allow for software to build higher abstractions. But in order to do that, we need solid underpinnings, and we need some sort of a translation layer between the two. And that should support network-wide transactions. If there's somewhere, I think it's a really exciting time right now, both in the ITF but also in many other standardization organizations, is the emerging idea or the emerging push for network-wide service models. The MEF has done quite a bit of work here. Cable Labs has done quite a bit of work. And there's a number of very exciting things happening in the ITF over the coming months. And this is all based on the fact that we now have Yang, and that we have at least an uneven distribution of NETCONF in the network, so we can start thinking about these things. And of course, the whole term SDN really helped people kick into this gear to realize what software could do for a network at some scale. Other requirements may be more minute, but also very, very important. We need to be able to allow the devices themselves to figure out the ordering. Even though I am currently an employee of Cisco, I have to tell you guys that one of the fundamental trickeries with the Cisco CLI is that there's an inherent ordering. If you want to remove things, you have to remove them in a particular order. If you want to add things, there's actually ordering to that as well. It is really, really irritating. And with NETCONF, we wanted to push this to the device, so we could send it valid but unordered data and let the device itself figure it out. That doesn't mean that we can't have references to things, so we wouldn't allow, for example, the references to security policies by name that doesn't exist, right? But at least we could send it as a lump, an ordered lump, so you don't have to do the ordering yourself in software. Minimal diffs. If we want to change bandwidth parameters for a VPN, there's no need to tear down the entire VPN and bring it up again just because we're changing a bandwidth parameter. We should allow for computation of minimal diffs between configurations, not to upset the instrumentation code running in the devices themselves. Again, a fairly pragmatic approach to something we know to be true in the way people implement the network elements today. And again, backup and restore. We believe that these things are just basic litmus tests of a management interface, both for human consumption and also for software. Again, validation of configuration, the ability to have a profoundly or a detailed enough schema before you send the configuration, allow for offline validation, and also offload the implementation on the devices themselves. And also at the network level, actually, kind of coming back to the idea that we could have service level models for basic things like VPNs or BGP policies that would allow for validation of endpoints, that would allow for correlation of data between participating devices, right? All in a formal and language-based way. And again, textual encoding, so this is something that we can use existing tool sets for, so we don't have to reinvent a completely new ecosystem of tools for this. Standardized data models, now it's getting interesting. Of course, everybody was very happy with bringing out the Yang language itself. It's an interesting exercise, takes a couple of years and probably something you wouldn't do one more time, right? But when it comes to actually standardizing the models themselves, much like we did with SNMP in MIB2, right? That's where the fun starts. And the reason why I exemplify here with interfaces data model is because that's one of the models that we have spent unbelievable amounts of time in, making sure that the model that we describe is something that fits the implementation of all the major vendors in the industry, which was not trivial, to put it mildly, because we don't want to constrain, of course, the implementation space of how you structure your interfaces in your implementation, but at the same time, we really think it's very compelling to have a single, well-known, standard and interoperable way of describing interfaces and how to configure them. Support for multiple configuration sets. This might sound minute, but it's actually pretty important when you do these things in software. We wanted a scratch pad. We'll go into this in much more detail, so you could make several sets of configuration changes that you validate over time, and when you're happy with it, that's when you push it to the running state of the device, right? So several configs, and then you commit it. This is something that exists and have existed in both Juniper and Cisco CLIs for a long while, and it's also a very valuable feature for the programmatic access. So you can have delayed and orchestrated activation. You can put things in place, you can validate them, but you can wait until you actually put it into action. Things that are usually kind of put on afterwards are things around AAA, right? So we would like to have a way of describing role-based access control using, of course, create, read, update, delete primitives that is both data-oriented, so you can express things like, well, junior engineers can only see customer-facing Ethernets, while senior engineers can see everything, including BGP configuration. But you may also want it to be task-oriented, so you can say, well, junior engineers are not allowed to reboot, right? So it's not just data, it is the actions as well. While senior engineers, they can do whatever they want. They can take down the entire cluster if they want to. So build a framework that would allow for RBAC policies across these data sets or across these data models, including tasks, including remote procedure calls. Okay, so the implications of this can be pretty profound. Traditionally, we have had no well-defined protocols. We have had no transactions. We have had huge amounts of ordering challenges, which means that people have mistyped things and taken networks out of order and still do that. Actually, to the point where this is I think the number is about $13 billion a year spent only on the last hop between the provisioning systems and the network elements themselves. And what we're going for, of course, is something that will allow for transactions, standard models, and standardized protocols, which will reduce, hopefully definitely reduce, the amount of time, money, and humans spent on typing things vastly, and more importantly, take out large parts of this cost base, which is again based on integration, which usually means ongoing programming, and put that into licenses on software that knows how to talk to these standard protocols or talk to these standard protocols and talk to these standardized models. So if you want to look for a very, very strong driver coming from the operational side of things, this is probably it. Any questions on the background? You all got it. That's great. All right, let's go into NetConf a little bit more. Okay. So of course it's a protocol, so we have a layering model. This comes back to the previous slides, right? In the bottom, we wanted to make NetConf protocol or transport protocol agnostic. So we actually allowed it to travel over several protocols. The ones that seem to stick, we had a couple of them in the beginning. We actually had SSH, we had SOAP, we had Beep, and a couple of others. The ones that seem to stick is SSH. That is what everybody is implementing. And it seems to be the case that this is the only security protocol or security tunneling protocol that service providers or large network owners, I should say, trust and have the capacity of understanding also for their security frameworks. TLS is really compelling, especially if you're going in both directions. So we're working on that as well. But as soon as we mention certificates, people tend to crawl back into where they were. So it's a little bit more, needs more work. On top of this transport protocols, we have an RPC layer. So basically not much more than an RPC and an RPC reply framing. On top of that, we have the actual operations. So here's where we go from a transport or envelope protocol into something with semantic value. Here's what it starts to tell you, that this protocol knows that it's doing things. It's changing configuration. So we have things like get, which means that you fetch the entire set of data on the box, both operational and configuration data. You have get config, which actually just, again, fetches the subset of the data that is related to actual configuration. We also have notifications. So I mentioned that there's also an asynchronous way for servers, which means the devices themselves, to send asynchronous notifications in kind of a pub-sub setup to the clients. And on top of this travels our precious configuration and state data. So you would wrap that into the get configs or the edit configs, and that's actually the meat, the things that we validate towards the Yang models. Conceptual databases, and I'll go through this again in the next session in some gruesome detail with a lot of XML and things flying over the wire here. But there's 3 databases, and most people with experience, again, from modern, for example, Juniper and Cisco devices will recognize this. We have something called a candidate data store, which I think of as a scratch pad. So when you start your session, the candidate data store actually usually has what's in the running data store, but you can change it to your hard's content without affecting the running state of the network element itself. So you can play around with that, you can edit it to your hard's content, you can continuously also validate. You can ask the box to take a look at the content of the candidate and tell me what you think according to the Yang module. So that's actually optional. You don't have to have that. What is mandatory is the running database. The running database is a conceptual then representation of what the box is actually trying to do, or actually doing in most cases. So it reflects the running state, both configuration and non-configuration data in the box. And then, of course, there's the startup data store, which is also optional, which is likely something that you would now and then copy your running configuration into. Because if your box cold or warm restarts, that's where it's going to pick its content from. So those are the 3 conceptual databases that NetConf kind of describes, where both candidate and startup are optional, and running, of course, you can't have a box without running. Capabilities. This is really also a very profound thing with NetConf, right? When you open up a NetConf session, both sides, both the client and the server, will expose its capabilities. What the client says is actually not very interesting. What the server says is actually what is interesting. So capabilities is basically a way for the box to describe what it can do, both in terms of protocol extensions, but also which data models and versions and deviations of the data models that they support. So this is the way for the box to, hopefully in a complete fashion, describe to the client how to talk to it and what it's got available for the client, okay? And we really wanted to make NetConf into a protocol that you could implement on very restricted platforms. So again, the mandatory set of operations, the mandatory set of things you have to implement to claim NetConf capabilities is very, very small. You can actually have a running database that would require reboots, right? So if you have very resource-constrained environments like your actuators and sensors and things like that, there's usually no reason for being able to manipulate the configuration, but rather change the configuration and have the box reboot, okay? So NetConf scales very well both up and down here. So the common operations that we have, the primary verbs, if you like, the primary features of the NetConf protocol. So get is the verb that you would use to fetch the entire or a subset of the data set of what's running in a box. Of course, you can filter for things, but get will give you both state data, operational data, and configuration data. You have get config, which will fetch only the configuration parameters. So if you're doing a backup, or if you're doing a rollback or setting up for a rollback, you would use get config, because it's something that NetConf will tell you that you can take this content that I'm giving you here from the server, put it to the side, and then you can use that as the content of a later edit config, okay? So it's always the case that the content of a get config is something that you can try and put back on the device later. Edit config is the verb to actually edit the configuration. Again, there are many versions of variants of this depending on which databases you have, and we'll talk about that in the next session. We have copy config, which is what you use to copy content between the databases, or actually also from URLs. So if you want to do things like copy this configuration from a TFTP server or HTTP server, you would use the copy config operation. Delete config is what you use to delete subsets of data or configuration data in any of the databases. Discard changes is something that's tied to the optional candidate database. It's a way of saying that whatever outstanding changes I've made to the candidate database, remove them and take the candidate database into sync with running. It's part of the set of operations that you would do if you're using locking and transactions. First, we have locking. The locking structure for the initial NetConf data or the NetConf protocol is very crude. Either you lock the entire database or you don't lock the entire database. There's no, at this point, useful, more fine-grained locking. Turns out that that's a very, very challenging proposal, and we are kind of working on it, but for now, locking is on the whole database or not. And the big tough part with this is that Yang, as we will see, allows for references across data sets. And it's very easy to build Yang models that would not allow you to do very fine-grained locking, because you would then lock things that were referenced and the referee at the same time, or partial logs covering partial sets of these references. It gets really, really tricky. So for now, we have to live with all or nothing locking. So of course, we have the commit operation. Commit literally takes the data that's in the candidate data store and turns it into the running data store. It requires that you have the candidate data store, obviously, so it's tied to that feature. And of course, you can also do a cancel commit. So we'll go through that as well. Commit can be done in a timed fashion. So you can say things like, commit this to the data store, to the running data store, and wait for a confirmed commit. And if I'm not back inside of a number of seconds, roll back. So that's also a fundamental part of the two-phase commit, right? But if you want to cancel that commit before the timer expires, you use the cancel commit operation. Schema management, and this is, again, also a fundamental thing, right? As part of the monitoring capability, there's something called get schema. So if you think about the fact that the device will expose to the client during its initial hello exchange the capabilities that it implements in terms of the Yang modules that it implements, it is up to the client then to say, okay, I actually have all these Yang models, so I understand what it's doing here, but that one is new, and I haven't seen it before. So we would use get schema to actually ask the network element itself to send back the Yang or XML schema model for that particular capability. Might also be the case that you reboot a router or a switch with a new set of features, new firmware. And the Yang models aren't new, but there's a new version, let's say, of the interface configuration Yang module. And you would realize that what you have on disk is now outdated, and you would use the get schema operation to fetch the new one. It is, again, a very powerful part, or potentially a very powerful part of the discovery mechanism of standardized, hopefully standardized networks. So when you find a new device, you open up a NetConf session to it, and you discover the capabilities. So instead of matching on product vendor name and product version, right, you would discover the capabilities described by the protocol and the Yang modules described in the protocol. So no more matching on vendor ID and no more matching on firmware revision. You would rather look for what features does it expose and what are the versions of the standard, hopefully, and also vendor-specific Yang models that you would discover. All right. So anatomy of NetConf sessions. On the left side, you have the very ambitious NetConf session, someone with a very ambitious way of thinking about how to do things. You would, of course, do the hello, which is mandatory. You would probably lock the running and the candidate database. You would discard the changes on the candidate so you know that you're starting afresh. You would edit the config on the candidate. You would probably commit confirmed, and you would probably go and do some tests while the confirming timeout is running. When you're happy with everything, you confirm the commit, and you copy running to startup, you unlock the candidate and the running, and you're done. A fairly watertight set of operations that actually covers many of the errors and the kind of failure cases that we see in traditional configuration management. But on the other hand of things, maybe you're running something very low power, and all you need to do in this case is to accept the hello exchange, and you send an edit config directly into the running database, and off you go. So at times we hear feedback saying that NetConf is too bloated or too ambitious. But again, the point here is, as a protocol, it literally scales to both ends, to very ambitious transaction-oriented networks, all the way down to very small kind of firmware or very small low-power devices. It all depends on the way you implement it. So the protocol doesn't force you into any of these models. So distributed transactions, this is where it gets really interesting, right? You want to do something across 3 boxes. You would connect to R1, R2, or R3 in this case. You would lock them. You would edit the candidate database with a commit with a timeout. And this is again where you do assurance checks. Maybe you want to see that a trace route goes through this new VPN, or you do burn-in tests for MEF services while the confirmed timeout is running. Or actually you make sure that you didn't configure away your manageability IP address, which is another classic, right? If any of these fails, you can tear down the session and the boxes will roll back themselves. Or if you lose the session, the boxes will roll back themselves. So nothing to do software-wise on the client side or on the management platform side. When you're done with it, or everything looks good, your assurance tests return success. You confirm the commit, copy to startup, and you release the logs. So anything that happens in here, again, this is very close to a very traditional 2-phase commit truly in the computer science database world. It covers most of the failure cases that are known in this domain. Okay, a number of common NetConf use cases, of course. All of these things do apply mostly to day-to-day operations, and it's something that we would expect from an ambitious protocol. Any questions about the NetConf protocol? Any questions? We all know it and love it. That's great. Let's go into Yang. So again, Yang, data modeling language, tree structured. We want it to be very close to the device instrumentation. So a lot of time spent with people under the hoods of routing and switching platforms to make sure that the constructs in Yang reflects what's running, both in proprietary implementations and also in kind of the commercially available routing stacks and what have you, right? So it's in fairly well harmonized with the running code that's out there. It's got a lot of features, right? It's a full-blown language. It's not something that you would use to express processes or something that would give you Turing completeness or anything like that. Again, it's a data modeling language, right? It is actually, it's protocol mapping independent. You know, people are doing quite exciting things with it. Of course, it came out, you know, we designed it to work hand in hand with NetConf. But we know of several implementations of which I've worked with at least 2 that allows Yang to drive not only a NetConf interface, but actually CLIs, SNMP. We have RESTconf that I mentioned here, web UIs, right? So it's our experience is that it's definitely rich enough that you're not tied to NetConf alone. I would even argue that the power of Yang is that it transcends NetConf, if you like. It is actually can be applied with many other protocols. So if NetConf for some reason doesn't really take hold, that doesn't matter that Yang is useless. It is the best step that we have for again, context-specific data modeling language to express configuration and state data in network elements. It's got a module content structure to it. And for people with a background in MIBs, we'll realize that, yes, we have borrowed quite heavily from there. Of course, you got a header information, you got metadata, like who's the author, what's the version, what are the prefixes for this. We got imports and includes, of course, especially for things like types. You don't want to reinvent what an IPv4 address is over and over. You can have your local type definitions if there's something in your module that requires that and you don't want to use the base types and the publicly available types. And then comes usually the meat of it, which is the configuration operational data sets or data declarations, which is the structure, syntax, and semantics of what you can do with a device implementing this Yang module. And towards the end, we usually group the RPCs, as I mentioned, the pings or reboots, the side effect-based operations, and the notification declarations. I mentioned that there's, again, is an asynchronous way for NetConf servers to send notifications in kind of a pub-sub model. So that's the overall structure of a Yang module. As I mentioned, the header metadata, important to understand here, or one thing that I'd like to point out is the revision statement. That is actually quite important and heavily used in Yang. It's actually supposed to also be reflected in the file name of a Yang module. So in this case, we can see that this module is named AcmeBox, and it's of revision 2014-412. So in this case, that file is supposed to be called AcmeBox at 2014-0412.yang, right? Because that will allow you to also see from the outside which version it is of. And the revision statements are also supposed to include a description, and there are firm advice on when you have to actually bump the revision, because the changes in the Yang file are such that instrumentation code can't really upgrade or downgrade using this. And another thing that's important here is that we make heavy use of namespaces. And this is, of course, borrowed from the XML world. And you'll see tie-ins to this. But the AcmeBox namespace here, I should probably use something like example.com here. But this is a string that's supposed to be globally and galactically unique to this module, combined with its version. So it should uniquely allow people to reference this module using a namespace. So data definition. So I'm going to kind of pick up the speed a little bit here. Leaf statements. This is probably the bread and butter, right? This defines a single value of a particular type, and kind of the nature of a leaf is that it holds no children. So it would be things like the IP address of an interface, the net mask of an interface, things like that, right? It's got types. We can declare things to be mandatory. You will also see here that it has a config true, which means that the top leaf has a config true, which means that this is configuration data, so it will be sent back on a get config. While the second leaf here, CPU temperature, obviously is not something that you would change using a client, right? It's something that's read-only, so that's config false. And you can also see that we can express things like units here. But again, leaves is at the end of the branch, no children to that. I mentioned some of the attributes. There are more. I'm going to point some of the more important ones out later. Leaf lists, so multiple values of a particular type. Things like if you allow for many IP addresses to the interface, then you would have a leaf list of type IP address, right? In this case, domain search, type string. There's ordering to this, right? Some leaf lists need ordering. So you can either have system ordered or user ordered. Depends on the nature of the data itself. And of course, there are operations then in ordered lists to insert things first, last, or before or after particular members of the list. Container statements are just that. They contain things, and it doesn't carry any semantic value except for the fact that containers can have something called presence. So for example, if you have a container, in this case, yeah, that's good. It's an SSH container, and it's got a presence statement saying that if you find this container in the configuration, that means that this box actually has SSH enabled. It also means that if the SSH container does not exist, and you can use NetConf for existence checks, it means that SSH for some reason is not available for this box. So it's an optional container that carries some semantic meaning. Lists, I guess, after leaves, I guess, is the big construct here. So list is, well, what SNMP people probably would call a table. It's a keyed set of data ordered as a list. For configuration lists, a key is actually required. If the list is not configuration, you don't have to have keys at all, because you might not be able to even key things into it. So you might be required to dump the entire list or the entire table at the same time. So putting things together, of course, this again, we will go into this in much deeper detail in the next session. We can express, again, most of the things that we've found to be true in network elements today. A number of constraints, kind of semantic and syntactic constraints, attributes for list and leaf list. You can have max and min elements, of course. Things like how many interfaces or how many IP addresses to an interface can be expressed by max elements. We can key things in different ways, and this is where it gets a little bit more interesting, and again, this will be also part of the next session. The key field is, of course, as usual, used to specify exactly which row we're talking about or which member we're talking about, and we don't allow two rows to have the same key values. But there's actually something called unique as well, so you can have a combination of keys and unique statements. So well, keys is the index, if you like. Unique is a semantic constraint that says for this set of items or this set of leaves, they need to be unique among the sets of members in this list. Multiple keys. Okay, so if you have multiple keys, in this case, for example, IP prefix pairs on an interface, of course, you can have the same IP but with different prefixes in some implementations of interface managers, right? While in that case, of course, only the IP and certainly only the prefix would not be sufficient to express uniqueness, right? So you can have multiple keys, basically a key statement with multiple leaves in it. And the key order is significant, right? So depending on whether the ordering is, you know, IP prefix or prefix IP, we're going to show things differently over the protocol. Leafrefs, this is something that database people usually call foreign keys. It's a way of referencing from a particular part in the tree to an instance in another part of the tree. So a valid leafref, of course, the entire concept of a valid leafref is that there exists a value for whatever it is pointing to, or sets of valid values for whatever it's pointing to. So this actually introduces a little bit of ordering. So a good example of this is, for example, name security policies. So name security policies can, of course, be referenced from configuration, for example, for interface context or verb contexts. So by using leafrefs here, we can ensure that if you're referencing a name policy, we check that that name policy actually exists. So in order to reference it, it needs to be created first. So if you're setting up a new policy and going to use it, you have to add the policy and then reference it. Of course, you can do it in a single transaction, but it won't allow you to reference non-existing policies. So it's a nice construct for referential integrity, and also doesn't, well, it allows us to avoid kind of dangling pointers, which is not uncommon in human-to-machine interfaces. And it's also the case then that you can't remove a security policy that's being used somewhere else. That would actually produce an error because it's not valid according to the data model. So in this case, we have a RIP routing subsystem that has a list of leafrefs pointing to existing interfaces, right? So the key being here that you can't really, for example, remove an interface in this case. So if you were to try and remove the interface by a particular name using configuration means, it would complain that that would invalidate the RIP configuration, right? So this is a specific example of that. And to make it more interesting, of course, at times you have to reference combinations of things, right? So for example, for a particular, in this construct, we have a container called video that wants to reference both an IP and a port pair. So it starts to get interesting in the second path here. What we want to do is pin this video parameters to an existing IP and port pair, but not to any IP or any port, but the pair. So the first path here is pretty straightforward. It's /client/IP. The second path is more intricate, right? What it actually does is that it says, I want to reference a list member under client that has the same IP that my sibling leaf has. So it resolves the sibling leaf, current VIP, current ... VIP port to mean whatever the VIP leaf points to, and then pins its own value to that port. Yes. Takes a little bit of thinking. But it's a clever construct that would actually allow you to then have multiple keys to single instances in external lists. Okay, and as I mentioned, we can use XPath, and there's actually the concept of deref here, which is also a very powerful construct. You can take an XPath and you can deref the value, and it reduces the complexity. If you look at the left side, we actually have a triple pointer. So 3 different, we did what we did in the previous slide, but now we're doing it on 3. And by using derefs on the right side, we can make it a lot easier to understand and kind of grasp. So it's a good, if nothing else, good syntactic sugar. And again, this is still on the server side. So this is the part, this is a Yang model that will be valid for a particular implementation, right? Grouping, of course, this ties into the reusability, right? So groupings are kind of like include statements. They're used for lumping together data sets in a named fashion so you can use them later. So in this case, address port pairs, of course, is an obvious thing for a grouping. And we can see on the lower left side how the container peer has a container destination that uses target. And of course, target is the name of the grouping on top. And of course, you can use grouping. You can have several uses statements on the same grouping. So it's more a matter of, if you like, modularizing or refactoring your Yang models into something that can be consumed by people more easy. And you can do refines. So refines is a way of saying, I like that grouping, but in this particular context, I want to add stuff. In this case, we have something called a target grouping with an address port pair. But the user on the right side says that actually for the way we use this grouping in HTTP, we need to add a default statement to the target port. So when we use this for HTTP, we're going to add the fact that the default port, if nothing else is mentioned here, is going to be 80. Import and include. Okay, so just quickly here. So it's all around namespaces, right? So you'd have module X, which has a namespace. And the big difference between imports and includes is that imports pick data sets from other namespaces. So you would import them by reference, which also assumes that you have access to that namespace during your compile step or your build step or wherever you're doing this. While includes is more like actually include statements in, for example, the C language. It sucks data into your current namespace, right? So it would typically be something to keep you from having super large files. Maybe you want to factor out things in separate files, but you want them to end up in the same namespace. While includes or imports is when you want to borrow, for example, data types from existing modules or the existing models. Everybody's kind of nodding. That's good. So submodules, again, as we mentioned, is something that you would then include. All submodules know what they belong to, so they actually point that out in their own declaration. It's through using the belongs to statement, because you can't import submodules. You can only include submodules. Okay, a little bit of types here. So actually, most of the type work that went into Yang came from the SMI NG crowd. So the people that had worked on a new and improved version of SMI. Types can be a horrible process. We were very happy to take most of their work and just put it in there, right? So we have base types and derived types. So base types is, of course, part of the Yang language itself. Derived types is something that the users would start with base types and then derive things out of. And then we, of course, we continuously publish what we hope are useful type modules. So for example, of course, we have the IANA interface set as a Yang module that you can download from the IANA website to the IANA environment. And of course, we have a number of basic Yang types for networking. So things like IPv4 address, like fully qualified domain name, and an IPv6 address, which, by the way, was surprisingly hard to define in a regexp, is already available, so no need to reinvent those wheels. The usual suspects, of course, integers, decimals, strings, enumerations, nothing that would surprise anyone. I think maybe the leafref, we mentioned that, is its own type, and we have less strict references like identity refs that we will cover in a little bit as well. And of course the empty type for things that doesn't contain anything, but maybe it's a presence container. You can define your new types. In this case, of course, we wanted a percentage type based on unsigned integer 16, but we had a max range of 0 to 100, so 16, of course, is a little bit wide for it. We describe it as percentage, and then you can just use that type in the same namespace without any prefixes for it. You can do restrictions, which is very useful, especially for string types. You can have disjunct ranges, so in this case, we have a base int32 type that is restricted to the value space between 1 and 4 and 10 to 20. We have native type limits available. So in the second one here, derived int32, we can have 11 to max, so you don't have to go back and remember what int32 max was. For strings, you can both constrain the length, if you like, the lexical length of things. So in this case, 1 to 255, but also have patterns. So we use regexps here. They're surprisingly powerful concept, right? And the important thing here, again, is to make use of this for offline validation. So before you send things, you can consult the Yang file for all the data that you want to send, and match it, for example, with a regex engine to make sure that whatever you're about to send is actually something that stands a reasonable chance of being accepted. It also, again, takes a lot of pressure off of the implementation on the network element side, right? Because, again, these are very well-defined and very well-structured, I'd say, constraint elements, which means that this fits very well in a data model-driven environment. So for the vendors that have implemented or invested in having their on-board management framework being data model-driven, this reduces the amount of coding quite significantly. Unions, of course, one of its member types. So in this case, for example, you would have a threshold that could be either a percentage or disabled. So you can have different types in the union, obviously. I mentioned the common Yang types. Yes, we got good coverage for most things you would expect, all the way from physical address or MAC address to IP address. That's a union of IPv4 and IPv6. So again, no need to reinvent things here. All well defined in RC 6021. RPCs and notifications. Okay, so I mentioned actions with side effects. So an RPC has a set of inputs and a set of outputs that are defined in Yang, okay? So you can, of course, this is like a call signature, if you like, or a whistle for soap, or whatever you want to compare with. It describes what we expect going in, and it will tell you how it will respond. Of course, the input in this case is a very simple thing. It's just an image. It's a single leaf, right? But you can, of course, have more structured inputs, right, to your heart content, depending on what this thing is doing. And the same thing with the output. In this case, it's a simple status string. But, of course, you could send back an entire data set of something, maybe an ordered list of traceroute results, for example, which is pretty common. And this, of course, again, is something that the client side can consume and understand how to form RPCs from. So again, things like the reboot RPC would be something that the device would expose through its Yang models. It's not something that you would hopefully not have to do magical incantations to do using other means, but it would be part of the complete set of Yang definitions in an ambitious implementation. Notification statements, again, I mentioned there are ways for servers to send asynchronous notifications in a pub/sub model. So in this case, we have a notification called config change, and it's got two different leaves here. First of all, an operator name, so maybe we're pointing out, maybe this is the beginning of a nice blame game implementation. It points out what's the username of the person who did this change. And here's a clever use of instance identifier. So in this case, we could actually have the notification actually contain the data set that was the change. So maybe a NetConf payload representation of what just changed. Maybe something inline, or you'd reference it somewhere in the box. So in this case, the instance identifier values would point to, in this actual example from an implementation, we would point out the data set, in this case the leaves and the lists that have been changed and what their new value is. So for an incrementally tracking, for example, inventory system, that would be enough to update itself based on an asynchronous notification from the network. And then, of course, you can go and correlate, but this should be enough for it to understand what the nature of that change was. Okay, let's head into the advanced stuff. There's one also very particularly powerful construct called must here. So a must statement basically takes an XPath statement and checks its validity on every commit or on every change. So it's a very powerful way of saying that these things must hold true, otherwise we will throw an error. So in this case, what we're checking is that in this case, we are checking that the retry timer, or actually the access timeout, is not bigger than the access timeout. Because if it is, we will send a message, right? We will abort the transaction, we will refuse the change, and we will just send that message back. And this must construct can be used for most of the things that day-to-day network engineers has on little pink worksheets beside their screen. Things like don't reuse IP address is something that you can normally trivially express with a must statement. So if an incoming edit config contains an IP address, we can look for its existence elsewhere in the data set, and if we find something, we can say, that's probably a bad idea. You're reusing an IP address, right? So there's a whole world of interesting semantic restrictions that you could use must statements for, that I think could be lifesavers in many instances. And again, these things, the way, of course, Yang is defined and the way these things are described is that as long as you can access the data set in the configuration, you actually don't have to check these things in the instrumentation code. You can do that in your data model-driven layered, the day's first questions. This is a big moment. So the question, hang on. The question was, is there a should to the must? No, not that I know of. What would the semantics of a should be? Strongly suggested? Kind of a please let me shoot myself in the foot thing. Yeah, that's not a primary feature of Yang. That is an interesting take, actually, more like a warning. You have to do things twice. You know, the should will trigger on the first attempt on the session. Interesting. That is suicidal, man. Don't do it. Absolutely, and you have to be careful with the must statements so you don't constrain yourself, too much, right? Second question.
So the XPath, the scope of things that you can access with that is just the one device, or are there constructs that can let you get out and kind of check consistency across a network?
So in this case, what we're talking about here, it's constrained to the local device. Where it really explodes in usefulness is what you mentioned. And that is service models in Yang, where you can check constraints across distributed devices. That's when it gets really interesting. But for this conversation, maybe that's Nanog 63. Talk about what service model Yangs look like, where you can check constraints across devices. And so, can you formulate that as a question? So I can tell it to the mic. I once even wrote a blog post about why that's not a good idea. So the question was this: is there a way to express constraints on operational data? Based on operational data. So on configuration based on operational data. So actually, most implementations that I know of won't stop you. But what's strange, and this quickly gets philosophical, of course, is that operational data in general you can't control. So your data set may become invalid asynchronously, just suddenly, right? So if you're referencing things that could be affected by operational state, the next second, your data might be valid. And that poses a really tricky situation for the server implementation, for the device implementation. What do we do? What do we do now that we know that a must statements doesn't hold? Who do we call and remind them that, oh, the operational state of something? But that's in the general sense, right? Of course, then you could argue, well, there are operational data that we do control, right? And that we could say, we trust the fact that it won't change spuriously. Right? But in a general sense, it's a dangerous proposition. Dangerous because, again, it can become asynchronously invalid. Just suddenly it's invalid. Okay, another must statement, of course, we can use clever things in XPath like summing. So sum is a primary feature in XPath. So if your favorite NetConf and Yang implementation vendor actually supports that, they hopefully have done things like made sure that, in this case, we look at the total weight exceeding the configured max weight. So again, this is something that can be done, but you have to remember that this sits on the device. So not only does it need to be expressed there, it needs to be supported there as well. But it does provide for a very, very efficient or very interesting ways of constraining stuff that, again, this can also be used for pre-checking, right? So before you send things to the network element itself. Augmentation, I mentioned that extensions is really, really important, especially to the vendor base, right? We want to be able to let people express what they do better around some basic features. So the way you use augment in this case, you use in the augment statement, you point out where in the data tree you want to graft on a new data tree. So in this case, we'll put under system user, we will put a new leaf called expire. That has a date and time type to it. So this taken in combination with the sys module will give a tree that where the users actually have an expiration of type, date, and time. So it's a way of decorating known or existing modules with your own extensions, if you like. And it's still on the positive side, so it's adding things. You don't use augments to take away things. And in this case, we actually added what's called a when statement. So in this case, which is another constraint, so you use when to check for particular things. So in this case, if the sys class of a particular user is wheel, then he can choose his own shell. The shell is configurable. Okay? If this sys user doesn't have class wheel, then the leaf shell aren't available, so you can't configure that at all. Choices, always interesting. So a choice allows one of several alternatives, and the difference between union and a choice is that a choice has structure to it. It's not just a set of types, but actually a set of substructures. So in this case, the transfer interval can either be in a frequency or something in this case that would say after each commit we transfer, right? So either a substructure with a particular unsigned integer or just an empty set, which then carries semantic value in the sense that the box will behave differently if you choose that. And of course, you can have multiple definitions. You can name them, or you can use containers and groupings for this. So a choice can actually have several cases. In this case, we will have a number of leaves for the counters thing here, and a container for warning only. And there's a default statement, right? So if you create the choice container or create the choice group, we can pick one for you. And this means that if you send an edit config, for example, to create these things, the implementation itself will put, in this case, the counters as the valid or currently active configuration. Identities. So here's a way of getting closer to what most of the people that are looking for object orientation looks for, extensible types, right? So in this case, we have physical interface. And we know that in our main or first module, we defined a couple of them. We have module physif. We have an identity called Ethernet. So that defines an Ethernet type. And then you have identity Ethernet 1G that is based off of base Ethernet. So this is ways of expressing, if like, some sort of inheritance or referential integrity going kind of up abstraction. And you can also, of course, borrow in. So if you have a separate module, in this case called newer, you can keep working on that base physif Ethernet and extend it to your heart's content. So this cuts across many things where you actually want to be open for extensions at a later stage. So interface types is a good example of that. Question number 3. Say that one more time.
So what's the sort of situation where you would use kind of identity ref for inheritance instead of using the augmentation, or just sort of adding existing class?
Right. So, for example, in environment, so not all data structures allow itself to be augmented nicely. So, for example, you can't really augment a list, right, to have new members. You can't augment a container, for example. So in that case, you would fold it into, you would fold it into identities and use those as types, right? But it kind of, it steps back from the very concrete, because of course, the fact that you have an identity carries some meaning, which then is pushed into the instrumentation rather than expressed. What does it mean to be an Ethernet interface? So you usually have, if you see identities, you usually have big description fields that describes the kind of semantic behavior. Other things are like things like crypto algorithms, where we can be sure that there will be new ones, right? That's one of the things that we can be sure about. But it doesn't really help to augment things into known structures. You would rather extend them and reuse them. Did that make any sense?
Yeah.
Thank you. Feature statements, I mentioned a little bit about that. So you can declare things like has local disk in this case. This is a feature. So the box can say that, you know, I have a feature called has local disk. It may or may not be available, right? And you can check for that later. So down in the system container, in the login container, you can check for if feature. So if has local disk is true for this device, then it will expose, first of all, a presence saying that you can enable logging because there's disk here, and you can describe the buffer size. And things that are in the standard models today are things like, does this box implement SNMP, right? Are there SNMP on this box? In this case, we can actually look for a interface index also in the realm of NetConf and correlate between SNMP and the NetConf realm, right? If it doesn't implement SNMP, then there's obviously no interface, or doesn't have to be an interface index, right? So it's a way of expressing what features the box is currently running, and to constrain, if you like, or expose certain parts of the data set depending on whether that feature is on or not. And it also has a lot to do with how many vendors are building their routers, right? And actually how many vendors are licensing their router software. Some features may not be turned on because of licensing constraints. Some routers may run on a particular hardware, so it's the same operating system, but it runs on a particular hardware form factor. Therefore, it's got a couple of features that's not available or that are available based on that form factor. And of course, many features that you have in the hardware-based platforms will have features that's going to be turned off in their virtual counterparts. When you run in a VM, you know, many of the hardware platform stuff will of course not make any sense at all. Deviations. So this is, fourth question. Go to the mic.
Is there a standard place that you go to look to find out what features a box has? Like when do you get the features on NetConf?
No. But there's a big difference between, and maybe I should put this in the speaker notes for the feature slide. There's a big difference between, what happens in the hello exchange, right? When the server describes what the protocol extensions it knows, what capabilities it has, and features that are local to a module. But it's a good point. Eventually that might be a good idea, especially for well-known modules. So if you augment in your own features, you know how to formulate and how to expose them. Because the way it is now, you actually have to parse and understand the Yang module for a particular part of the data set and draw your own conclusions, which is a manual step. So, deviations. So this is this is something we reluctantly introduced. We realized that all implementations can't support all full standard models, even if we try to do the standard models very constrained and very pragmatic. So vendors can implement something called deviations. So deviations can actually be the extension that you use to actually replace or remove or add things that will break the semantics of a known module. So of course, it's a way out, if you like. We haven't seen much of this yet. Might have to do with the fact that there aren't massive amounts of implementations, and we will likely see it. The big question, I guess, is whether people are going to declare their deviations or just silently deviate. And of course, in the standard sense, we want to try and push them to at least use deviations to explain to clients what's the difference between the exposed or published model and what they're doing. Any more questions about the Yang language before we hit the kind of finishing notes on what we're doing with Yang? All right. A couple of things happening. Most of the actions around the language itself and its core modules currently happens in the IETF, although there are a lot of activities being spun up in, for example, I work with the Open Networking Foundation around virtual switch management for OpenFlow. That's actually based on NetConf and Yang. There are MEF standards for performance and fault management in Yang. There are Cable Lab standards for CCAP in Yang. TM Forum seems to be picking it up. So a number of activities going on across the industry, but the most tangible stuff is happening in the IETF. And for the NetConf working group, for the protocol side of things, what we're working on is RESTconf. And we'll talk more about RESTconf in the next slot here. I'll show you what that looks like. It's basically using REST to manipulate data described by Yang. We're working on a NetConf call home protocol. This will hopefully take a stab right at the horrible situation we have with discovery in the industry today. Discovery, as you all know, right now is ping sweeps and MIB walks. If we could build a secure and robust call home protocol based on NetConf and SSH, that would be huge. The good thing about it is that it would be open, standardized, and hopefully interoperable. So you could reduce the amount of call home protocols you had down to something that resembles one. That'd be cool. NetConf over TLS is great for companies that actually has a certificate infrastructure in place. So we're advancing that. We're looking at ways of teaching network devices where to go for their NetConf server. Might be using the HTTP v6 options for this. There's a whole lot of debate whether XML is efficient enough for protocol encodings, right? Some people would argue that XML is bloated. So we're looking at ways of perhaps mitigating that, something called efficiency extensions. Schema conformance is something that comes over from SNMP. It's another way of describing exactly how you implement certain Yang modules and what your inheritance tree looks like. Timed operations. You might want to say, here is what I'm going to put in the candidate, and you should trigger this at my maintenance window, which is 1 a.m. local time. And in the NetMod working group, so in the language working group, we're working on Yang 1.1. It's going to be backwards compatible, so this, I don't have to rewrite this entire presentation, but there's bits and pieces, of course, that we've learned over the 8 years that we've had Yang now. We want to be able to configure SNMP. Sounds ironic, but it would be great if we had one entry point also to set up SNMP. One of the big ones is models for routing management, or for managing routing protocol implementations, I'd say, and of course the usual suspects being ISIS, OSPF, BGP, and everything that comes after that. So big, interesting, heated debates in the IETF around that. We want to leverage the experience that we have, so we're writing guidelines for authors and reviewers. And if there's something I would like to put out to this team, of course, it's come help. Now that we have what we believe is a good and expressive and robust language with several implementations, now we need to go work on the standard models. There's something called the Yang doctors in the IETF. They're always looking for people that are very interested. We have the Sundays before the IETFs cut out to actually sit down and help people with models. There's actually a GitHub put up for the work that's being done right now in the IETF under that URL. So get digging if you want. We would very much appreciate more people spending time with this because we want the kind of second generation Yang models to be very good here. A lot of RFCs available. This is more for reference. And thank you. Any questions, or we send the kill session? Thank you very much for your patience. Thanks a lot. See you back in half an hour. Let me just reiterate that the actual hands-on, or where you'll start seeing PDUs flying, is in half an hour. So I guess go get something to eat or drink and come back, and we'll open my terminal window and let it rip.